Hello everyone. As pipeline design may be hard for beginner, I will give you another design example. That is the set calculation example. So in this section, we will talk about the design specification, that is the design requirement of set calculation, and I will analyze the pipeline, analyze the choice of the pipeline for this design. Then we will talk about how to verify the design, that is, we will analyze the test points of the design. So what is set calculation? Okay, the whole function is in this equation. The function is you have to calculate the set, that is the sum of absolute difference of two 16 by 16 array. Each point in the array is a 8-bit unsigned integer. So you will calculate the difference and the absolute value for each point, then accumulate the totally 256 points together to get the set result. So this is the function. Okay, this is a useful function. This is a piece of operation in video encoder, such as the H.264 and 265 video encoder. We usually use this equation to find the most match block. When encoding a frame, we usually use this equation to find the most match block in the reference frame. So this is the value of current frame. This is the value in the reference frame. Okay, if you have understood the equation, let's go on with the design specification. This is the block diagram of the block. Clock reset, data input, and current image data input, and reference image data input. So you will have 60 by 60 pixels and 8-bit for each pixel, so it will yield to 2048 bits. Then along with the input, there is a enable signal. Yeah, this signal is indicate whether this cycle the input is valid or not, and you will have the output signal send and a valid along with it. Okay, a small question for you. Why the output of set is 16-bit wide? Can you figure out it? Why? Okay, this slide will show you the relationship of each pixel in the input array and the 2048 bits. So the upper left pixel is in the lower bits, then we put each pixel from left to right and from top to down. Then the last pixel, that is the pixel with index 15 and 15, will enter the most significant bits. Okay, let's check the sample waveform. This is the waveform for input. So when there is a high value and call enable, there must be some values in the D-in and ref input array. Then you have to calculate the SAD of the two. Then after some latency of cycles, after some latency of cycles, you will assert SAD value and give the SAD value for this group. Also, we require that for any input, you will have the fixed cycle of latency. So the latency for this input and the output should be the same. Okay. Also, for this input, the latency from this input to this output, should be the same. Okay, this is the sample waveform, and the value of call in is random, so it can be any value for any cycle. Okay, this is the design requirement. Can you think about how to design this function and try to make it run as fast as possible? That is, try to maximize the clock frequency of your design. How to do it? Please think about it. Okay, you can pause the video and I will go on. First, you have to analyze the calculation flow of the function. So the calculation flow is two array of inputs, then sub for each pixel. Then you have 256 subtractors, in parallel. You can do it in parallel. Then get the amps value of each point. So there is also 256 absolute operation in parallel. Then you will accumulate all the points together to get the final SAD output. So this is the calculation flow of this function. So after the analysis of the calculation flow, you can get the idea of the hardware architecture for this function. Add amps, then accumulate. You can do it in a single cycle. That is, you can use pure combination logic to implement this function. But how about the logic delay? How about the logic delay for this implementation? Okay. So the logic delay may be very, very big and you will get very low clock frequency. Then the throughput of the whole design will be low. So how to increase it? So the method here is insert pipe stage to break down the combination logic. So here we get the idea of how to pipeline a design. I have explained it before. So the first key point is you have to figure out the architecture of pure combination logic. Something like that. Then you have to estimate the logic delay of each operation, such as the delay of here, and here, and understand the design requirement of clock frequency. Then you insert DFFs into the combination logic at proper location. That is, you have to try to divide the combination logic pass to EQ logic delays. Then you can maximize the clock frequency of your pipeline design. For example, if we assume the delay of this operation is 5 nanoseconds, about 5.2 nanoseconds, okay? But this is very big, okay? There is accumulation of 256 data. Then we assume the delay is around 25 nanoseconds, okay? Okay. So if you just insert a DFA here, okay, you can see that the delay of the first part is 10.2, while the last is, so this part will be the critical path, the delay critical path. This part will finally decide the maximum clock frequency the design can run at. Yes. This is the clock frequency the design can run at for megahertz. Yes. So for this pipeline of design, the logic delay of each segment is not equal. Okay, this is not a good pipeline. This is not a good insertion point of pipe register. Yes. Okay. Okay, so the key point is you should have the pure combination logic architecture of the function. Then you have to estimate the delay of each operation. So how to estimate the delay of each operation, such as the delay of sub, amps, accumulate. Yeah. We have explained it in chapter 1 of this course. Yes, the arithmetic datapath section. Okay, if you have no idea of this, you can come to the arithmetic datapath section of chapter 1. Okay, let's try to pipeline this design. So the first solution is, so we don't think pure combination logic is a good solution for high-speed design. So how about two stages of pipeline? We just finish it in 3 cycles. Insert 2 stages of pipe registers. Yeah, this will be much better than the one before. Yes, 5 nanoseconds, 5.2, and 25. So this design, the clock frequency will be decided by the delay of this part. That is about 40 megahertz. So the next step is, if you want to further increase the clock frequency of the design, you have to pipeline this part. Yes. So how to pipeline this part? Can you figure out it by yourself? Okay, there is some solutions from me. First, we can think about, can we accumulate 16 data in a cycle? That is, you have an array of 6 by 6. Sorry, an array of 16 by 16. Then we first accumulate the 16 data in a row. Then we will make an array of 16 by 1. Yes, this is the first stage. This is the amps value. Then in the second step, we accumulate the 16 values of the column. Then we get the final result of SAT. So in this method, we further divide the accumulation to two pipe stages. So the longest logic delay here will be accumulation of 16 data. Okay, if you still satisfied with this solution, you can further pipeline the accumulation part. For example, how about just accumulate of 8 data in a cycle? Yes, accumulate this 8 data in a row. Then you will get an array of 16 by 2. This is the pipe register. Then you can accumulate 8 data here in a column. Yes. Then you will get the array of 2 by 2. Then accumulate the 4 data together to yield the final result. So in this method, you pipe this part with 3 pipe registers, with 3 stages of pipe registers. So the longest logic delay here will be accumulation of 8 data. This should be smaller than the accumulation of 16 data. Okay, by the way, do you have any idea of how to do accumulation of 8 data? Is you have to use 7 cascade ANDers. Sorry, yes, 7 cascade ANDers. Or you may say you can put there in the tree architecture. Yeah, the binary tree architecture. About 3 levels. Yeah, it's something like that. Yes, if you think so, okay, you are wrong. Okay, you must have forgot or missed something also in the chapter 1 of this course, Arithmetic Datapath. There is CSA, carry save under architecture, for the accumulation of multiple data. Okay, you have to review this part. Okay, so this is the idea here. Accumulate of 8 data for each cycle. Then if you still unsatisfied with the delay of here, you can further pipeline the design of the accumulation part. For example, you can try to accumulate just 4 data in a cycle. Yes. This should be something similar. Okay, I just show you the figures. 16 by 16 yields 16 by 4. Then 16 by 4 yields to 4 by 4. Sorry, 4 by 4. Then 4 by 4 yields 4 by 1. Then you get the final result. These are the pipe registers. Okay. So if you still unsatisfied with the delay here, you can further choose to accumulate just 2 data in a cycle. Yes. And can you compare the delay difference of 2 data and 4 data, 8 data, and 16 data? Okay, let's let's analyze the critical path for this architecture. Which stage do you think which stage is the critical path stage? The first stage, the second stage, the third stage, and the fourth stage. Which stage will have the longest logic delay? Can you figure out? Yeah, they are all accumulation of 4 data, but the data weights is different. Yes, here the input is 8-bit, and for here the input should be 10-bit. Yes, and there should be 12-bit, and this will be 14-bit. The final result will be 16-bit. So this stage must be the critical path, because it's accumulated for data of 14-bit. Yes, the delay of 14-bit must be bigger than the delay of 12-bit and 8-bit. Yes. Okay, so this is the critical path. Okay. Okay, from the decision of me, I choose the accumulation of 4 data architecture. Okay, so this is the pipeline diagram for this architecture. That is for this architecture, the pipeline diagram. Okay, this is the cycle number. So each cycle, the first cycle I will do the sub operation of each pixel. So there will be 246 subtractor here working parallelly. Then the next cycle I will do absolute operation. So also 256 amps operation here working in parallel. Then I will accumulate 4 data in a row and use the 16x4 array. Then accumulate 4 data in a column. Then use the 4x4 array. Then accumulate 4 data in a row. Then in a column, get the final result. And also you can check, and also you can check the operations for different input for a same cycle. Yeah, the latest input and the sub stage. Then the one cycle before it will be at the amps stage. Then the 2 cycle before this will be at the first accumulate stage. Then the 3 cycle before will be at the second accumulate stage. Yeah, for a single cycle, each stage will do operation for different inputs. So, do you have any question on the pipeline? Why you can pipeline a design in such manner? For example, for this cycle and this cycle, the register value, the register value after the value of the registers after the subtract operation, the value of this register has changed. While after some cycles, you can get the right you can get the right result for the first input. Yes, the value of these registers, these registers in the arterial queue or in the circuit is the same register. Yes, the value here, the value of this register at cycle 0 and the value of the same register and cycle 1 has changed. Yes, but we still get the right result for the first input. Why? Okay, this is because, to my understanding, at this point, at cycle 0, after cycle 0, although the value of this register has been changed, but you already has all the information to calculate the final result. That is, you already get the apps value of each point. So at cycle 2, for first input, there is no need for you to get the difference value of input of the first input. Yes, you just get the absolute value is enough for you to calculate the final result. Yes, and for this cycle is also the same for this cycle. And this cycle, there is no need for you to get the difference value after cycle 0. Okay, you just get the accumulated value. The accumulated value is already has all the information to calculate the final result. Yes. So the answer is, after each stage, actually you has all the information to calculate the final result. There is no need for you to keep the value of stages before. Okay. So this is the idea of why pipeline can work. Okay, let me explain why I choose the accumulation of 4 data in a cycle architecture. The first, when designing a design, or when architecture a design, you need to give more budget to logic delay. That is, if we want to run 2 MHz for this design, okay, we write this in the design specification, and when you architecture the design, you can't estimate that the delay is around 5 nanoseconds. Okay, you can't estimate it like that. You'd better estimate that the delay for this part is about 4.5 or 4 nanosecond. Yeah, you have to get more budget to the logic delay. This is because for the digital IC or IP design flow, you architecture it, and then coding it, then simulation it. Then you will check whether you can run at 200 MHz a lot at synthesized stage. Yes, synthesized stage is in the later stage of the whole design flow. So if you finally find that your design can't run at 200 MHz at synthesized stage, this is sometimes a little late. So you have to reverse back to re-architecture your design, recoding it, and verify it. This is time consumed. So at architecture, you have to give more budget to the logic delay. Okay, the second reason is next pipe stage. Then you may add more delay to a stage or all stages. Then you will use less pipe DFFs, yes, but this doesn't definitely result in small area. That is, you use less DFF doesn't definitely result in small area. You will think, why? I use less cells, why I can't get smaller area? Okay, this is the reason. As you have increased the logic delay of a stage, yes, so the synthesizer tool may choose big cells for the same function, such as for the LED function. LED, okay. Sorry. Law, okay. Law, for law, okay. Such as for the law, input law function. Law operation of two inputs, okay. I have explained in our first chapter, there is cell with driving strength of 1 and cell with driving strength of 2. And even two input of law function with driving strength of 8 or maybe 16, okay, or 4. So for these cells, it has small delay but big area. They are the function same but delay different and area different. So if you increase the delay of a stage, the synthesizer tool may choose bigger cells to implement the same function to meet the delay requirement. Yes, you set the delay to the clock frequency to 200 MHz and 5 nanoseconds for each stage. So the synthesizer tool, to meet the 5 nanosecond delay requirement, the tool have to use the big cells. This is the first reason. And the second reason is, as you increase the delay of a stage, the synthesizer tool may choose faster but area bigger architecture for some basic arithmetic function. For example, the AND function. Okay, we have explained there is many architecture for AND, such as the ripple AND, the slowest but smallest area. Slow but small. And the carry look head AND. This is faster but much bigger than ripple AND. And you have the tree AND, such as BK tree AND. This is even faster but even bigger. Okay, so this is the reason. Decrease less pipe stage, increase delay in a stage. Although you use less pipe DFFs, but it doesn't mean the area of whole design is smaller. Okay, and for high-speed FD designs, the wire delay will usually take about 50% to 64% of cycle time. That is about, for this case, so the wire delay may be in a time of that range. So this is a big part for a cycle time. So you have to take care of that. So more data converge to a point often lead to longer routing of wires and cause large wire delay. So when 16 data is converged to a point, and 8 data is converged to a point, and 4 data is converged to a point, this should have shorter wire delay. Okay. Okay, that's why I choose the accumulation of 4 data in the reference design. Okay, that's all for the analysis of this function and the analysis of the architecture. And finally, let's compare the performance for hardware implementation and the software implementation, such as you can write a C program and run it in the most advanced 64-bit Intel or AMD CPU. Yes. Let's compare the difference of the performance for the two implementations. Okay, for the hardware implementation and the architecture we choose, I suppose it can run at 200 MHz for 160 nanometer process. This is a little old process in these years. And the total and sub operation in a second is about, you can figure out the sub, absolute, accumulate, yes. Then we run at 200 MHz. Then we'll yield mega operations, yes. Then this is equal to 143.4 giga operation per second. Yes, this is a this is a little, yeah, this is a big number. So let's check the performance if we implement the same function in CPU. Okay, we assume the most advanced 64-bit CPU can run at 5 GHz. As it is 16-bit data wireless, we assume it can do 8. Okay, it can do 8 and observe an AMPS operation of 8-bit data in each cycle. So for a single core, the performance is about 5 GHz and 8 data. Yes, and 8 data. Either 8 and 8 serve or 8 absolute. So the performance is just 40 GHz operation per second. So you can see the small design you design here has outstanding the performance of the most advanced CPUs. Okay, but this is just a single core. Yes. If you consider if this operation can be divided into multi-core of the CPU, usually the modern CPU may have 8 or 16 cores. Yes. Okay. So for this slide, you may come to know that the performance difference of ASIC and hardware and CPU and software. The software is, or you can say the CPU is instruction-based operation. It has to fetch instructions and do operation according to the instruction it fetched. And in each cycle, it can do limited operations. This is limited by the ALU inside the CPU. Yes. But for ASIC, or you can see the digital circuit we designed, the operation, this is not instruction based. Typically, they are data flow based operation. Yes. when data is passing through these registers, yes, the operation is done on these data. So we call this data flow computing. Data flow computing, and we can put many and serve or other operations in a single cycle. So that's why the ASIC implementation can outstanding the most advanced CPUs. This is the reason. Even we usually run at lower clock frequency, but the performance is much better. Well, we can't laugh at the CPUs. Okay, the CPU is a general purpose processing unit. That is, it can do many different things or many different jobs. You just change the program, then it can do many different things. But for our circuit, yes, we just can do SAT calculation. If we want to do something else, such as something like what? Okay, anything. Okay, anything except SAT. The circuit can't work. Yes, the circuit can't work for any operation other than SAT calculation. Okay, so that's the difference. This is more general purpose, and the ASIC design. The ASIC design is more specific. Okay, and for modern CPUs, there may be vector operation instructions. Okay, so for these instructions, if they can operate data of vectors, so the performance will increase dramatically. So what is vector operation instruction? Oh, you can Google it. Okay, let's analyze the test points for our design. There is some test point I listed. For example, you have to cover the minimum and maximum value of each point for the input array, yes, and the accumulation, such as so this is the accumulation, yes, and you should cover the minimum and the maximum value of SAT result, yeah. Then you should cover the different waveform of call enable, as this wave and this signal is random value as the specification. So you may generate the waveform of 1 to n consecutive ones, followed by 1 to n consecutive zeros. So how to choose the n value? Okay, you have to decide it. Okay, for example, if we set the value of 1 to 8, so you may test the case of consecutive 1 cycle to 8 cycle of active cycles, then combination with consecutive 1 to 8 cycle of inactive cycles. Yes, that is 1 followed by 1 to 8 inactive cycles, 2 consecutive active cycles, followed by 1 to 8 consecutive inactive cycles, 3 active cycles, 8 active cycles, followed by 1 to 8 inactive cycles. So this will be 64 test cases. But if we set n to 12, then you will have, this will be how many? Yes, maybe some number like that. 1450 test cases. So how to choose the right number for this design? Okay, you need consider it. How to choose the proper number of n for this design. To my opinion, we should cover the pipeline latency. Yes, we should cover the pipeline latency. So I may choose some number around 8 to 10. I think 8 to 10 is enough for this design. Okay. Okay, one note for you. Please include a reference design, or you can say reference model in your test environment and can check the result of DUT automatically. Okay, there is some explain. If you read the reference code, there is some explain for the reference code. In the reference code, I use parameter to define the data weights of input array. So this is used to enable the code reuse when there is just data weights change for other applications, such as if we want to do set calculation for the input of 10 bits or 12 bits, we just need to change the parameter. No need to modify the whole design. So you can change the parameter and the instance of the module. Yes, just give her, replace the 8 with 10 or 12. Okay, I have explained the usage of parameter, the parameter syntax in chapter 2 of this course. Okay, that's all for this section. There is a homework for you. Please implement the set calculation function in Verilog using the accumulation of 4 data architecture. And please design the test environment to verify your function. Yes, please don't look at the video and do lesson. Practice coding, simulation, and debug. This will help you to grow very quickly. More practice, more progress. Thanks.